For Unit 3, FRQ4, Part A is asking us to indicate whether the position of x2 of block 2 when it comes to rest is greater than, less than, or equal to 3D. So I drew out the picture, and so this is block 1 at the initial position, and then when it's compressed to here, it gets launched to the position 3D, and is given to us that block 2 has a greater mass than block 1, big M greater than little m, and it is also told that they're both compressed to the same position, so negative d. And so I said that the position of x2 is less than 3d because since the block has more mass, the friction exerted on it is greater for block 2, which means the position reached will be less than the position block 1 reach. And so I got 2 out of 3 points for this because I indicated correctly that x2 is less than 3d, and I said that a larger mass means a larger force exerted on block 2. But in order to get the third point, I need to indicate that that the initial energy is the same in both cases, or that the speed of the block at x equals 0 is smaller for block 2. And this is because since they're both compressed to this length, that means U sub s is the same for both, and so is MEI equal MEF. U sub s will equal to 1/2 mv squared. And since we're increasing the mass for block 2, but it will still equal to the same U sub s, which means that in order to make it the same, the velocity will decrease, so we'll have a smaller speed for block 2. And that's how you get the third point. For part B is asking us to start with a conservation of energy or the work energy principle, derive an expression for the final position x2 of block 2, express your answers in terms of m, k, d, mu sub k, and physical constants as appropriate. Begin your derivation by writing a fundamental physics principle or an equation from the reference booklet. So for this problem, I didn't start out with a physics principle or equation, but I still got the answer correctly because I said that once I got the U sub s is equal to 1/2 k delta x squared, and so it is equal to the work done by friction, which I didn't really indicate, and I found that friction is equal to mu sub k times mg, and I plugged it back in, and I got this, which is the right answer. So I got 1 point for getting the correct answer, and I got another point for substituting mu sub k times mg into friction. So I got 2 out of 3 points for this. But in order to do it properly, I'll restart. Let's start out. It's a non-conservative problem because there's friction. So MEI is equal to MEF, and so the initial is still U sub s, which is equal to 1/2 k delta x squared. Or wait, since this non-conservative problem is MEI equals MEF plus work done by friction, and so this will be equal to kinetic energy, so 1/2 mv squared plus the work done by friction, and since the block is being pushed into the surface with friction, this gets rid of the k. So 1/2 k, and is delta x in the problem is d, so 1/2 d squared is equal to work done by friction, and then what's it called, the work done by friction is equal to the work done by friction is equal to mu sub k times Fn, and since the y position doesn't move, Fn is equal to mg, so Wf equals mu sub k times mg, and so you plug that in, so 1/2 k d squared is equal to mu sub k times mg, and you just move it all the way to one side, so k times d squared divided by 2 mu sub k mg, and that will equal to the position of x2 or block 2, and that's how you get all 3 points, because you substituted the friction and you started with conservation of energy, and you got the correct expression. For part C, is asking us to justify how the expression to derive for x2 you derived in part B is or is not consistent with the claim made in part A. So I said it is consistent because if you claim made by part A, I said that if you increase the mass, the position will be less, and as you can see here, if you increase the mass, since this is on the denominator, if you increase the mass, the value will just be less, so it is consistent. And I got 2 out of 2 points for this because I explained how the relationship between the mass and the final position is consistent with my part A. And I addressed how the mass of the block and the final position of the block